Hello and welcome my dear students. In the last class we did some numericals. I hope you all understood it well. If you liked it, please share it with your friends also so that I get little bit motivation. And okay, so today we are going to discuss not about electric current, some effects of electric current. Because of the electric current, there is an effect which can be seen called as magnetic effect of electric current. And the person behind this was also a Professor Hans Christian Oersted. Okay, remember his name, Hans Christian Oersted. This name at least you have to remember. Professor Hans Christian Oersted, he was a physicist as well as a professor. One day when he was getting ready for his lecture, on his table he had all his books and some electrical circuit, and on the other side there was a compass needle, a compass needle which gives us the direction, always points it always points towards a north-south direction. So all this thing was ready on his table, it was kept on his table, and as Oersted was getting ready for his lecture, he was searching some books. He was taking the books. He picked up that compass needle and he kept it beside the circuit. The circuit was closed. That means the current was flowing through the circuit. Okay. So he kept the compass needle and he kept it beside the circuit. He saw that all of a sudden the needle started deflecting. The north and the south direction, the north and the south pole, those points that used to deflect. He just neglected that. Later on, he kept the compass needle back to its previous position. So again, it deflected and then it came to a rest. It was pointing towards north-south direction. As he wanted to go for his lecture, he did not bother much and he went for the lecture. As he was taking lecture, this thought all of a sudden came into his mind. So when he kept the compass needle close to the circuit, the compass needle showed deflection. Then he started thinking, okay, that means I have to think a little bit more on this. And that day led us to the discovery that Oersted told us that whenever there is electric current passing through a conductor, side by side there will be a magnetic field created. Whenever there is electric current in the conductor, magnetic field is also created along with the electric current. In the previous class, we had learnt that whenever there is electric current in a conductor, the heat energy is also given out. Heating effect of electric current. Today, we will learn another effect of electric current which is called as magnetic effect of electric current. So, Hans Christian's experiment proved us that electricity and magnetism are closed concepts. Okay, they both are related to each other. So let us take this topic into detail and learn few things. Okay, let us first consider, he considered an electric circuit, no? So let us consider a conductor, a conducting wire, then the terminals, the key, and okay. This is a circuit, a simple circuit I took, no resistor, nothing I have taken, a simple circuit. So when the key was closed, and you had a needle, a compass needle, let us suppose this is north and this is south. Whenever there was an electric current flowing through the circuit, this needle showed deflection. The needle deflected. The north pole of the needle moved. It deflected. All of a sudden it moved. Whenever there was no current in the circuit, key is open means no current. The north side, it came back to its north-south direction. Whenever there was current passing through the circuit, the needle deflected. That means, when will a needle deflect? When will a compass needle deflect? A compass needle will deflect, the north pole will deflect when there is magnetic field created. when you have magnet around, at that time, if you bring a bar magnet towards it, that time also the needle will get deflected. So when here there is no magnet, but electric current is passing and the needle deflected. This means that electric current is producing magnetism. Electric current is producing magnetism. Understood? Now one thing, first thing you understood. Now, second, whenever you change the direction of electric current. Now here, the direction of electric current was this side, this direction. Okay? Now I will change the direction of electric current. That means the positive terminal came on to the other side. Now the positive terminal came on to the other side. Now here, the direction of electric current will be from this side, no, opposite side. Positive, down, and then goes up. So in the earlier condition, the needle deflected this way. Now in the later condition, when the direction of current changes, the direction of magnetic field also changes. Electric current changes, the direction of magnetic field also changes. So when the current was flowing from left to right, the needle showed deflection in one direction. When the direction of electric current was changed, the deflection of magnetic compass also changed. That means if the electric current direction is changed, the direction of magnetic field also changes. Okay, so write down the first point. If the direction of electric current changes, the direction of magnetic field also changes. Note it down. Okay, this is the first thing that you learned from this experiment. Okay, what you have to remember? First you have to write the name of the person behind this magnetism. The intensity of magnetic field is given his name. We call the intensity of magnetic field as Oersted to honor Hans Christian Oersted. Okay, now the next subheading as magnetic field through a current carrying straight conductor. Magnetic field through a current carrying straight conductor. What is that? Very simple. Let me explain with the help of a diagram, circuit diagram. Let us consider a current carrying conductor. That means a wire, a copper wire. We'll consider a copper wire. Let it be connected to a resistance. Okay. We have a resistance. In the textbook, if you see this sign, it means the resistance can be changed. You have a resistance box. In that, you can change the resistance. 10 ohms, 20 ohms. Okay. Like that variable resistance we can supply. Then we will show an ammeter. Okay. Okay. Then this is connected to a terminals of a cell, positive and negative. Then we have the key. Okay. And now comes how to detect whether magnetic field is produced or not. Magnetic field can't talk to us. No, yes, I am present. Magnetic field, I am present. Like that. Yeah? So for that we have a trick. We have a trick to find out whether magnetic field is created in this circuit or not. What we will do? We will take, now this is the wire, no? So through the wire we will take a cardboard. Suppose we take a cardboard and through that, on that cardboard we'll make a hole and this wire we will insert. Okay, so this wire we will insert through the hole. So that wire is here. So here I'll keep the cardboard. So cardboard will be kept in this way. Now the wire will be inserted through the cardboard and remaining part will be connected to the circuit. Okay. So now here the circuit is complete. Now I will not hold it this way. We will show it in the diagram. So this is our cardboard. So here is the cardboard. Okay. So here is the cardboard which I was talking about. This is the cardboard that I was talking about. So here we have the positive terminal and here we have the negative terminal. Electric current, conventional flow of electric current is from positive to negative. So electric current is flowing, coming down. Okay. Understood till here? A simple circuit. And we have a cardboard. Why is this cardboard kept? For decoration purpose. No, to detect whether magnetic field is created or not. So on that cardboard, what will you sprinkle? Cardboard. On the cardboard, you will sprinkle some iron filings. When there is no current flowing through the circuit, the iron filings will be scattered around. As you have sprinkled it, the iron filings will be on the cardboard. As soon as you switch on, that is, as soon as you close the circuit, the current starts flowing. You will see that the iron filing starts arranging into a concentric circles form. The iron filings start arranging into concentric circles form. This become bigger and bigger. You will see that the iron filings arrange themselves in the form of concentric circles. That means magnetic field is created in this circuit. Understand this? From current carrying straight conductor, what all things are you learning? You have to draw the diagram. What all things will you learn? You will learn that as I increase the electric current, suppose as the potential difference increases, current also increases, no? Ohm's law. For 5 volt, there is a magnetic field created. I increase the electric current, the magnetic field also increases. As I increase the electric current, the magnetic field, the concentric circles formed are also more. Okay? They confine together. When the magnetic field is less, you don't get a perfect concentric circles. Somewhat concentric circles you will get. When the magnetic field is maximum, the concentric circles can be seen distinctly. That is the first thing. What is the first property? As the electric current increases, the magnetic field also increases. Electric current and magnetic field are directly proportional to each other. Learned? Okay, things you learned. You learned that as the electric current increases, the magnetic field also increases. Okay, understood? Now, every time for the iron filings to behave this way, it should be connected in this circuit. Now, I am doing another thing. What I will do is, I will again bring our compass needle, okay, compass needle, north south needle, and I keep it beside this circuit. When I keep it beside the circuit, if there is current flowing, the needle will deflect. Now with this needle, I will move little bit far away. As the distance increases, I will see that the needle deflection decreases. That means, if the circuit is kept in this room and the needle I am keeping it in another room, will the needle deflect? Will the magnetic field will be felt everywhere in this room? No. The magnetic field will be felt just beside the electric current. That means, as the distance increases, the magnetic field, will it increase? Magnetic field will be felt where there is electric current produced. Whereas in another room, if I am sitting in another room with the needle and I am saying, why this needle is not deflecting? Circuit is present in this room. Will the needle deflect? No. As the distance increases, the magnetic field, yes, decreases. As the distance from the circuit increases, you have to write it down, second point. As the distance from the circuit increases and the current is unchanged, because if you increase the current, magnetic field will increase. As the distance from the circuit increases and the current is unchanged, the magnetic field will decrease. Okay? This is the second thing that you learn from this current carrying straight conductor. Direction of current is in the downward direction. The magnetic field direction you show it in this way. Why is it this way? We will discuss it soon. Okay? For the time being, you show the diagram in this way. Keep in mind these two arrows. Current downward, the magnetic field is in sideways, this way. Okay? Now let us discuss the magnetic field through a circular loop. Through a straight wire we discussed, through a straight wire. What will happen through a straight wire? You sprinkled iron filings. When electric current passes through a straight wire, the magnetic lines of force are produced. We understood this from the direction of the iron filings. Now let us talk about a circular loop. What is a circular loop? Don't take tension. Same cardboard I'll take. Now instead of one hole, I'll put two holes on this cardboard. Through one, I'll insert. Okay. Then I'll insert it down, and then from there again I'll insert. So you will get a loop-like thing. A loop-like thing like this. A loop of n number of turns. Now here you can see two turns of wire. So wire wound in circular form is called as a circular loop. For example, from here I'll take wire. I'll put the wire through the first hole. Take it, insert, second. Like that a loop is formed. A circular loop is formed. What will happen when you have a circular loop? Now remember, for a straight wire you had only one conductor, one hole. No? Here you have two holes, and through both there is a conductor passing through. So how will it behave? What is formed here? Let us learn it with the diagram. Now let's start. Consider the cardboard that we are using. Let this be the cardboard, and we have two holes on that cardboard, and we will insert a wire in the form of a circle. Is nothing but circular loop. So this is having n number of turns. Suppose we take 2 turns of wire. So the remaining part is shown here down. Remaining part of the wire is coming from the downward direction of the cardboard, and that we will connect to a circuit. So for a circuit we need a cell, an ammeter to check whether electric current is passing or not. To measure the amount of electric current. This is the loop. This is the setup. Now here we will sprinkle iron filings like before. When there is no current, the iron filings will be as you sprinkled it. When there is electric current through the circuit, whenever there is electric current through the circuit, at each point of the loop, here, this point and this point, you will see that there is concentric circles formed. At each point, there is concentric circles formed. And the circles are becoming bigger and bigger as the distance from the loop increases. That means as the distance from the loop increases, we all already learnt that the magnetic field will decrease. Here, beside the loop, when you are close to the loop, this point, the magnetic field is maximum, and as you go away from the loop, the magnetic field is decreasing. Understood? And here, as you see, onto the center of the loop, somewhat the magnetic lines of force became straight line. It is looking like straight line. So you will show the diagram this way. Here both points concentric circles, and in the middle you will show the lines to be little somewhat straight. Labeling. In the labeling you will show this as magnetic lines of force. Magnetic lines of force. And this you will name it as circular loop. Okay. Suppose they will ask you what is this, label it circular loop, and here we have the circuit with ammeter, key and all. Okay, understood? Now from this what do you learn? From straight conductor you learned two properties. From circular loop what did you learn? We learned that as the number of loops increases, suppose you have n turns of loop, each turn is contributing towards magnetic field. More the number of loops, more will be the magnetic field produced in this circuit. So if it is a straight conductor, magnetic field will be produced. But if you have n number of turns of a conductor, now here you have two turns. At both the points you have magnetic field created. So more magnetic field, more number of turns. As the number of turns of the wire increases, magnetic field also increases. This is one thing that you learn from this. This is one thing that you learn from this setup. Understood now? Okay. Now the time has come where we will predict the direction of magnetic field. Remember, no, in the previous figure I told you, you put the arrow. We will discuss about it later. Yes. Let us discuss how to predict the direction of magnetic field. Again, it was given by a rule. It is called as the right hand thumb rule. Okay. Right hand finger rule. Okay. It is called as right hand thumb rule. So all of you keep your right hand free. Okay. Keep your right hand free and your thumb. Okay. Such lovely thumb you have, right? Okay. So take the right hand thumb rule. Take your right hand and imagine that this thumb is the conductor carrying electric current. Imagine that this thumb is the current carrying conductor. Imagine that this thumb represents current carrying conductor. So here the direction of thumb is in the upward direction. So if the direction of current is in the upward direction, then the direction of magnetic field will be the direction of the fingers curled. Suppose. So we will imagine that current carrying conductor is the thumb. Then as you turn the fingers towards the conductor, turn the fingers towards the conductor. So my fingers are coming towards this direction. So the direction of magnetic field is in this way. When the current is in the upward direction of magnetic field is in this way. This is called as right hand thumb rule. So you have to write it down. Imagine you are holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of the electric current. Then the fingers turned towards the conductor gives the direction of magnetic field. Thumb, direction of electric current. The fingers turned towards the conductor gives the direction of magnetic field. So simple, no? Right hand thumb rule. Now let us bring the thumb downward. This way. If the direction of current is in the downward direction, where are your fingers turning? Your fingers are towards this direction. So the magnetic field is in this direction. That is going towards, now this is this direction. So when the direction of current is in the downward direction, your fingers are turning in this direction. That means the magnetic field is in this direction. When the current is down, magnetic field this way. When the current is up, magnetic field is inwards, this direction. Understood? Now same rule we will apply here and we will find out the direction of magnetic field. Let us first consider on this part of the loop. Okay, where is the direction of electric current? Upward direction. So your right hand, don't use your left hand now. Right hand. So here right hand direction of electric current means upward. So thumb upward. Now just see where is your direction. What is the direction of magnetic field? The turned fingers. No, this way. So this way means the direction of magnetic field will be this way. This way. Okay. So arrow you will put. Now did you understood why I put arrow that way? Please check. If it is wrong, you correct it. Okay. So when the current is in upward direction, magnetic field will be in this direction. So I put the arrow this way. Now let us see on to the other side of the loop. Here on this side, what is the direction of electric current? Downward direction. So your right hand thumb is in downward direction. When the thumb is in downward direction, where is the magnetic field? This way. This way. So the arrow will be this way. Understood? Here understood. Understood right hand thumb rule. So you have to draw the diagram, show the direction of magnetic field by using right hand thumb rule. Learn it well as given in the textbook. This right hand thumb rule, as I discussed, where you have the conductor carrying electric current, if its direction is in the upward direction, magnetic field will be in this direction. Right hand thumb rule is also called by another name. It is also called as Maxwell's corkscrew rule. Screw rule. Like you have a screw, for every pan you can see a screw, or anywhere you can see screw. Now when you put the screw inside, when you put the screw inside, for example, let me consider this. Suppose this is a screw. When I put the screw inside, that means I am turning it in clockwise direction. When I turn it in the clockwise direction, so that clockwise direction is the current. When the screw is turned in clockwise direction, the screw goes inside. That means the magnetic field is inside. When it is in the clockwise direction, magnetic field is in the inside direction. When I am applying the screw in the anti-clockwise direction, that is anti-clockwise direction. So this way, that means I am taking the screw out. So just to see how the screw behaves. When you take the screw out, when you apply current in the anti-clockwise direction, the screw comes out. That means the magnetic field is in the outward direction. Once again I repeat, right hand thumb rule also has resemblance to screw rule. It is also called as screw rule. When you put the screw inside, that means you are applying current in the clockwise direction. Magnetic field is in the inside direction. When the current is in clockwise direction, magnetic field is in the inside direction. Screw goes inside. When you apply electric current in the anti-clockwise direction, that is when you are taking the screw out, when you are removing the screw out, that means current is in the anti-clockwise direction. The magnetic field is in the outward direction. Clockwise direction, magnetic field inside. Anti-clockwise direction, magnetic field outside. This is called as Maxwell's corkscrew rule. Okay. This little bit also you keep in mind with right hand thumb rule. Okay. Children, so what all things we learned today? We learned that electric current and magnetism are closely related to each other. Who gave us this theory? This was put forward by Hans Oersted. Okay, remember him and respect him. Then we learned what about magnetic field produced in a straight conductor, diagram and two properties. Magnetic field produced in a circular loop, diagram and properties. As the number of turns increases, magnetic field increases. Then we learnt about the third, the most important thing, that is right hand thumb rule. You have to write it in your book and there is a diagram given beside. That also if possible, draw it down. I hope you understood the topic well. In the next class, we will take this topic ahead and we will learn about electric motor too. Till we meet for the next time, please take care of yourself. Bye.